Yeah. Hello, everyone. I hope you can hear me. Could somebody unmute? And
yes, we can hear you.
Thank you very much. That will be my routine, probably at the beginning of every lecture. Yeah, so today I would like to continue to teach about the electric field. That was done in Physics 1801, and in previous lecture I reviewed that concept, but I would like to do it again because it's a very important concept. So every charge produces electric field all around it. And when we put another charge into that electric field, then there is a force acting on that charge. Like here we put, let's say that capital Q produces electric field all around, and we put charge Q0, positive charge Q0, we call it a test charge, then there will be a force acting on it. By Coulomb's law, these two charges repel, and there will be force acting on Q0 along now the line connecting these two charges. And that force will be large if the electric field is large, and of course, if charge Q0 is large as well. So Michael Faraday a long time ago defined the electric field as the force acting on that test charge Q0 divided by the test charge, so that electric field, as you will see in a minute, is actually independent of Q0. But this is the definition, that electric field is the force exerted on that test charge Q0 divided by that positive test charge Q0. So the direction of electric field is the same as the force acting on positive charge Q0. And the unit of electric field is the Newton per Coulomb, now, quite often, we will first calculate the electric field, or electric field will be given to you, and you have to find the force acting on the charge which we put into that electric field. So then from this definition, of course, force is equal Q times E. And of course, if we put positive charge into electric field, and these black lines represent electric field, if we put positive charge, that blue charge, the force acting on it will be in the direction of electric field, right? Because the force acting on positive charge is now in the same direction as the electric field. But if we put negative charge, let's say this red negative charge, the force on it will be in opposite direction to electric field, because electric field is defined for the positive test charge. So I will be explaining a little bit about now forces acting on charges in electric field later on in the course. But any questions so far about this definition of electric field? If you don't have any questions, then I take this as a good sign. And on the next slide, that was done now on Wednesday as well, that if we want to calculate the electric field produced by a point charge or spherical charge, let's say capital Q, if this is capital Q, positive charge, then the electric field we can find from the definition as the force acting on positive test charge. So if this is, that red one is positive test charge, then the force acting on it by Coulomb's law is now given by this expression K Q times Q0 divided by R squared, where R is the distance between that red charge and that source charge. And as you see, Q0 cancels. That will always be the case. Q0 cancels. So electric field is independent of Q0. Q0 only serves to define and find that force and define the direction of electric field. So that source charge, which I designated capital Q, produces electric field equal K capital Q divided by R squared. So at every point around the charge, we can use this formula to calculate electric field due to a point charge or spherical charge. If the charge is spherical, that R is the distance from the center of that spherical charge. So here you see now the electric field vectors at different points, always radially from the positive charge. And usually we represent the electric field by drawing these continuous field lines, electric field lines, which show the direction of electric field, which is always originating at positive charge and going radially and radially away from positive charge. For the negative charge, if charge is negative, like here on the right-hand side, then if we put positive test charge now around it, somewhere close to it, the force acting on that positive charge will be towards the negative, because negative charge will attract that positive charge. So electric field will be towards the negative charge, So here you see the vectors at different points pointing towards, radially towards the negative charge. And these are electric field lines due to the negative charge. So all of that was done, of course, in physics 1801. Now, last time on Wednesday, I was also explaining to you that the electric field due to line of charge, let's say wire, charged wire, we can find using the result which we derived in previous lectures, that the force acting on certain charge Q0 located close to that charge line is given by this expression, 1 over 2 pi epsilon 0 Q0 lambda divided by R, where lambda is the linear charge density on that line of charge. R is the distance. R is not the radius. R is the perpendicular distance from that line of charge. So by definition, electric field is F divided by Q0. You substitute this expression for F here. And as you see, Q0 will cancel again. And electric field due to line of charge is given by this expression. Depends on the density of charge and, of course, on the distance from the line of charge. So I will be using this expression in the future as well. So again, continuing my review, and then we use the definition of electric field to find the electric field produced by the plane of charge. And in the previous lectures, we found that the force acting on charge Q0 located now at certain distance from the plane of charge is given by this expression. So by definition, electric field is equal F divided by Q0. I substituted the force, and again, Q0 will cancel, and electric field is just sigma divided by 2 epsilon 0. So electric field is independent of the distance from the plane of charge and depends just on the density of charge, right? Density of charge on the plane. If density of charge on the plane is large, electric field will be large, but is independent of the distance from the plane of charge. So that was that result will be needed in future lectures as well. So that much was done on Wednesday, but today I would like to calculate electric field produced by a ring of charge. So here we have a uniformly charged ring. Let's say that the linear charge density on that ring, very thin ring, linear charge density is uniform, right? Well, charge is distributed uniform. Now, in this particular case, the total charge on the ring Q is given. Capital Q is the total charge on that ring, and the radius of the ring is capital R. So here you see, radius of the ring is capital R, and the total charge on the ring is capital Q. Of course, if somebody would like to calculate linear charge density lambda, that would be equal total charge on the ring by the length of the ring, which is circumference of the circle, 2 pi capital R. That would be the linear charge density of that ring. Capital Q is given, R is given, so you could find the lambda. But in this case, I will find electric field at point P in terms of capital Q and capital capital R, but not in terms of lambda. But of course, this is the relation between capital Q, R, and lambda. So please, whenever you solve problems or whenever you review lecture notes or textbook, then it's very important to understand the meaning of different quantities and understand and it's important to understand what the question is. So here we have again that ring, and we will calculate electric field at point P, which is located distance Z above the center of the ring. So let's say the ring is on the flat table, and you calculate electric field at point P just above the center of the ring. It's distance Z. So Z is not variable. Z is just the distance. I call it Z because in my calculations, I will use now, again, X to be horizontal, actually maybe, and Y would be perpendicular to it, and Z is perpendicular to that ring. Okay, that's how I selected coordinate axis system. So Z axis is vertically up. Now, so here's the radius of the ring, and the first part to calculate electric field is to divide the ring into tiny elements, tiny chunks, and one chunk of the charge is here designated, you see, colored, and that charge on that element of the ring will be dq, and let's say that the length of that little chunk of charge is dl. So dq approaches 0, dl approaches 0. So this is kind of a very tiny element of the ring. And that element of the ring we can treat as a point charge, right? Because now dl approaches 0. And that element produces electric field at point P in this direction. You see, along the line connecting that charge dq to point P. So because that charge on the ring is positive, I forgot to mention that capital Q is positive. So everywhere on the ring, the charge is uniformly distributed by this positive charge. So that electric field will be away from that positive charge. And I designated that electric field by symbol dE. That's differential electric field because that dq is approaching 0. So electric field dE will also approach 0. But the direction is like you see. Now, it should be now very clear that the total electric field due to entire ring will be along the Z axis. Why? Because you see, for every element of the ring, let's say on this side of the ring, I can find symmetrically located element, say charge on opposite side of the ring. And this element of the ring would produces electric field along the line, connecting this charge dq to point P. So this electric field would be more or less in this direction. And as you see, I can also decompose that electric field also into electric field perpendicular to Z axis and parallel to Z axis, like I did, you see, with this electric field, I can decompose into this component and perpendicular to Z, and this component parallel to Z. And it should be clear that these two elements of the ring, this one and symmetrically located on opposite side of the ring, this element will produce electric field in different directions. By these perpendicular directions, this and this component will cancel each other because they're in opposite direction. But these components parallel to Z axis will be parallel, so they will add. So it should be clear that the resultant electric field due to entire ring will be parallel to the Z direction. Okay, I have written this here and with bold letters so that we have to calculate only the Z component of that electric field. So any questions so far about this illustration, that figure here and my explanation so far? Any questions so far?
I have a question.
Yes, please.
In the beginning, why did you have to substitute small r? Since small r is going to be constant, would that make the calculations easier if you leave it like that?
Very good comment. I have not mentioned that lowercase r yet, but your question is about lowercase r, which is a very important question because remember, capital R is the radius of the ring, but that distance from that chunk of charge dq to point P I designated by lower letter r. And like the student is saying that r, lowercase r, will be the same for every element of the ring. You see, this is also r because I hope you can see the cone, that P is like the vertex of a cone. And so this distance from every element of the ring to point P will be the same. So R will not be variable, R will be constant in this calculation. And that, like you've mentioned, that will make calculations very easy. In addition, I designated here this angle theta. So this is like that vertex angle for that cone. And that angle theta is also the same, because for every element of the ring, if you connect every element of the ring to point P, the angle between that R and Z will be equal theta, and it's constant. But I did not give you value of R, lowercase r, or angle theta. I just gave you a radius of the ring and Z value. So what is given is very important. I should have maybe written that given in this equation for this question are Z, capital R, and of course physics constant like epsilon 0. But of course, if you know Z and R, you can use this triangle, which is right angle triangle. This is 90 degrees here. And you can easily find what is lowercase r. This is written here actually. Lowercase r, you can find using Pythagorean theorem that lowercase r squared is equal capital R squared plus Z squared, right? And the angle we could also find using either sine function, tangent function, or so it's easy to find theta because Z and R are given. So that was a very useful comment. But I have not mentioned previously about lowercase r because I wanted to mention about that lowercase r at this stage, that you see this little chunk of charge dq produces electric field dE of this magnitude, maybe I could write that dE, this magnitude of this vector is equal that Coulomb constant K dq divided by R squared. That's the magnitude of the differential electric field, right? Because this little chunk dq we can treat as a point charge, and just a minute ago I was explaining to you that a point charge produces electric field equal EKQ divided by R squared. Now, because that charge I designate dq, the electric field I designate dE. dq approaches 0, so dE should be approaching 0 as well. Okay. And then, but in this expression, I also found the component of that electric field, which is in this direction, component along the Z direction, this component. See this component, because this angle is theta, and this is 90 degrees, then dE is hypotenuse of this triangle here, and component along Z-axis would be, component dZ would be dE cosine theta. So here I substituted for dE, K dQ R squared cosine theta. So this is just Z component of the differential electric field dE. So any questions about this important step?
Could you explain that again?
Yeah, I can explain this again.
Yes, please.
So, so you see, this is that little chunk of the ring. The charge on that chunk is dq, and we treat that dq as the point charge. And on the previous slide, I was explaining to you that electric field due to point charge is given by this expression. That point charge produces electric field using this expression, K Q divided by R squared. But in this case, because my charge is dq, I call it dq. And this electric field produced by that chunk is along this line, connecting point P to that charge. Remember, electric field is away, radially away from that charge. So here, this is the radial direction from the charge. This will be the direction of electric field produced by charge dq at point P, which is distance r from it. And this electric field, I designate dE. So I call it dE because the charge is very tiny. So the electric field will be also very tiny, and I call it dE. Then I found the component of electric field along Z direction, because this electric field, you see, makes this angle theta, that vertex of the cone angle, and this are theta. So then dEz, the component, Z component, is equal dE times cosine theta. Why cosine? Because that Z component is adjacent to that angle, okay? And then this I substituted for dE, and then I got this expression. So this is my starting point, that just one tiny chunk of the ring produces electric field along the z-axis given by this expression. I hope I did answer your question.
Yeah, I'm just a little bit still unsure why it's cos. I just don't see how.
Yeah, because this angle here is 90 degrees. This is the 90 degrees. And DE, which is this, is hypotenuse in the triangle. And this is DZ, DEZ, adjacent. Okay, this is 90 degrees. Right, and cosine is adjacent, which is DEZ, divided by hypotenuse, which is DE. Right, so okay. Cosine theta, of course, is adjacent, which is that component of electric field DEZ, divided by DE, which is hypotenuse. Okay, oh, yeah. But what you probably have hard time to see is that this angle here is 90 degrees. So if you make a model of a cone, and if you show the direction of electric field, then you will see that, you know, if this is the direct, if let's say this is the z-axis like this, z-axis, this is that DE, then the projection that DE projected onto z-axis here must be projected perpendicularly. So this angle here is 90 degrees. So if you make that model, then it will be very clear. But this angle is 90 degrees. This is very important. Okay. So then this is that expression for DEZ.
Thank you.
Yeah, you're welcome. So now, as I've explained previously, R is constant. Lowercase r is constant. It's not a variable in this expression. And this angle theta is constant as well. So because, as I've written before, given are only Z and capital R and capital Q, these are given quantities, then I want to express my answer in terms of these given quantities. So here I've expressed lowercase r in terms of given capital R and Z from this triangle. From this triangle, this is 90 degrees. Lowercase r is hypotenuse, and Z is one side of the triangle, and capital R, radius of the ring, is other side of the triangle. So lowercase r squared is capital R squared plus Z squared, and cosine theta, which I need in this expression, is just Z, which is adjacent to theta, divided by lowercase r, which is hypotenuse, right? So Z over R, but R we found here, R squared. So R is just square root of capital R squared plus Z squared. So if I substitute this for R and this for cosine theta, then that Z component would be written like this, right? I substitute for R squared, I substitute for cosine, and here you have the same R squared plus Z squared, and here square root R squared plus Z squared. So that will give me exponent 3/2, right? Because 1 plus 1/2 is 3/2. So this is the expression for the differential force DEZ. And as I've mentioned already a few times, Z is constant. It's not a variable. And capital R is constant. Z is constant. So the only variable in this expression is Q. Some of you would probably do what is done in many textbooks in physics, that you can find now the total electric field by integrating this expression over the entire ring. And in many textbooks, this is written like this, that because Q is the only variable, you take all constants, which are all of these are constants, in front of the integral, and you integrate over dq. And quite often it's written in the textbook that no limits of integrations, they take from 0 to capital Q, and that integral over all charges along the ring is capital Q. So this is the final result. So, this written like this, the final result is correct, as you will see. The only problem is that that integration of a lowercase q is not formally correct. Sometimes we do it in first year courses to now simplify calculations, because Q is uniformly distributed over the ring. So it's not that Q changes along the ring. So when you integrate, you cannot really integrate over Q. So the proper way to do integration is to do the following, that we have to express this variable dq in this in terms of kind of a proper variable, like, for example, this angle alpha. So please listen carefully, because there are two angles now. There is this angle theta, which is constant, but this angle alpha is this angle. I will measure this as the angle alpha when you go around the ring. So the angle alpha will be the angle, let's say, between my, let's say, if this I make x direction and perpendicular to this y direction, and z is perpendicular to it, then that alpha will be the angle in xy plane now going around the ring. So if I designate this angle, this as alpha, that would be a proper variable. But then I have to find the relation between dq and alpha. And that relation I can find using this proportion. I was explaining this in tutorial notes. Remember, tutorial notes were canceled, but I recorded tutorial notes and posted that Zoom video, that Zoom recording on eClass. And I encourage you to watch that Zoom video for tutorials, in which I now explain something about the rings as well. So I repeat this again, that if dq is tiny part of the ring, and if that arc length on which that dq is located, I designate by symbol dl, so dl is the length of that little chunk of the charge, then I can write proportion dq, because lambda is uniform, right? Lambda for the ring is constant because charge is distributed uniformly. So lambda can be written as dq over dl, and lambda can be also written as capital Q, the total charge on the ring, divided by the total length of the ring, which is circumference, 2 pi r, right? So capital Q divided by 2 pi r is lambda, and dq over dl is lambda. Then from this proportion here, dq can be written in terms of now dl. But instead of dl, which is little length, instead of dl, I have written here r d alpha. So if that little chunk of charge subtends the angle here, this angle, which is called d alpha, this little angle is designated d alpha, right? So you know from the definition, and maybe I should repeat this again, that for all of you said, you know that very well, that if I have a circle of radius capital R, then when I take the angle theta in radians, if this angle is theta in radians, and if this arc length subtended by this angle I call L, then angle theta in radians is just L divided by radius of that circle, right? That was done in high school and of course calculus, and which means that L, that arc length, can be written as R radius of the circle times theta. Theta must be in radians, not in degrees. And then dl d theta, the derivative is equal R, because R is constant, right? So dl d theta is equal R, which means that dl from this expression can be written as R times d theta. The only regret now I have that I should have called this not theta, but alpha. Okay, so because this angle here, so now change that theta to alpha, here to alpha, this theta changed to alpha, this theta changed to alpha, and this changed to alpha. I regret now, I should have used that symbol alpha, not theta. Then of course, dl is equal R d alpha, which I have written. If this is not clear, please watch the tutorial video where I explained this as well. So
Hey, Professor, I have a question.
Yes.
Sorry, I apologize for interrupting, but you know how you said that the first derivation isn't formally correct? So would we get marks off, or would we not be able to use it, or do you have to use the second derivation? I'm just curious. I'm fine with either or.
Yeah, that's a very good question, though, because many students, of course, are thinking about the marks on tests. And so, yeah, I prefer that you do proper way. That's why I explained that now. that integration over dq is not really formally correct, although gives correct result. The result will be, as you will see, the same, of course. But yeah, I prefer that you do it like I do right now to get full mark. So good question.
Thank you, Professor.
Yeah, thank you very much. Yeah, so if you have questions, yeah, you can unmute yourself. Students are very respectful. I so far so good. I'm very happy how.
Sir, I have a question.
Yes, please.
How did you get the 2 pi r?
2 pi r is circumference of the circle, right? So the length of the remember that lambda is density is the total charge on the ring by total length of the ring. So what is circumference of the circle of radius capital R? Circumference is 2 pi r.
Okay.
Yeah,
so you're using the total charge and dividing and
by total length and divided by total length. That gives me linear charge density lambda.
Okay.
And that lambda would be correct here because that ring is now extremely thin, right? Very, very thin ring. So yeah, so here that lambda would be correct to use.
Okay.
Yeah.
Hello, Professor.
Yes, please.
Sorry, one more thing. In the lecture slides that you posted ahead of time, I'm looking, it says dq over dl is equal to q over pi r. Is that a typo and it's supposed to be 2 pi r?
Yeah, it should be 2 pi r. So
okay,
I caught my mistake when I was reviewing my lectures, and I posted new lectures. Actually, I made a few modifications, and I posted a new lecture, that PDF file, just before I started this lecture. So if you copied the lecture notes, a couple of days ago, then maybe you should print the new one to avoid any confusion, because I made a couple of tiny typo mistakes. So this is now all clean, I hope, without any mistakes. So if I could come back now to my derivations. So if I substitute for dl r d alpha, see, if I substitute this, then we will get the relation between dq and d alpha. So let's go step by step. So from this proportion, dq is equal capital Q times dl. You have to cross multiply, divided by 2 pi r. Instead of dl, I substituted this r d alpha, and now I have converted dq variable into alpha variable, where capital Q is constant, of course, 2 pi is constant. Now, some of you might use this proportion right away, which is correct, that if you use proportion, because the charge is uniformly distributed on the ring, so then the proportion dq to d alpha, where d alpha is this tiny angle subtended by that dq. Remember, this is that angle d alpha. This angle is d alpha. So dq to d alpha must be in the same proportion as total charge on the ring to the total angle subtended by the ring, which is 2 pi radians, right? The whole angle 2 pi. So from this proportion, you could find also that dq is equal q times d alpha divided by 2 pi, the same result as here. So these two proportions are correct, of course. But I was explaining about that the dl is equal r d alpha, because this is part of so many different exercises, different problems to solve, that you should know all these little tricks which I'm explaining right now. So anyway, in short, dq is equal, given by this expression, which I substituted here, you see? Right, I substituted for, in this expression for this dq, I substituted this, I changed the variable from q to alpha, and now that z component is given by this expression, and I have to now integrate over the angle alpha. And I took all constants in front, and I repeat for the 5th time, z is constant, capital R is radius of the ring, constant, and 2 pi is constant. So I took all constants in front of the integral. I integrate over just d alpha. And the limits of integration are, alpha will change from 0. Let's say I mentioned, if this is my x direction, and if I measure, and this is y, and I measure that angle from this. So alpha will increase from 0 to 2 pi to 2 pi. So limits of integration will be 0 to pi over d alpha. And integral d alpha is alpha, of course. And then you substitute upper limit, which is 2 pi, minus lower limit, which is 0. So 2 pi and this 2 pi and this 2 pi will cancel. And then the final result of electric field due to the ring is given by this expression, where instead of K, I have written 1 over 4 pi epsilon naught. Okay, and then you have Z times Q divided by this R squared plus Z squared to 3/2.
Where did
So yes,
alpha go?
3/2?
No, the alpha.
Alpha, well, because integral d alpha is alpha, right? Like integral dx is equal to x.
Yeah.
Right?
So
and then you start with upper limit, which is 2 pi minus 0. 2 pi minus 0 is 2 pi, and then this 2 pi and this 2 pi will cancel. That's why that 2 pi disappeared.
Oh, okay. Thank you.
And I would like to ask you to rederive this solution, rederive this again at home. I got the notice on my screen that my internet is unstable. Can you hear me well still?
Yes. Yeah,
Okay.
it just cuts out every now and then.
Yeah, okay. Yeah, thank you very much, because I got that note, so that worries me a little bit. So hopefully everything will be okay until the end of the lecture. So that's the result, which is, of course, you don't have to memorize this result, but you have to know how I did derive this expression. You should be able to repeat all these calculations. So it's very important that you are able to draw that ring and use the variables. Of course, you could use different variables instead of Z. You can call it H or whatever, but you should be able to derive this expression. So I want, before I go
Sir, I have a question.
Yes.
So for the last part, can you explain the d alpha?
Okay,
part?
so I do here on the side, what is the integral d alpha? Yeah, the definite integral from 0 to 2 pi. Well, the integral d alpha is equal to alpha, right? And then you have to substitute the limits, upper limit and lower limit, like you did in calculus classes. So this is equal what? You first substitute upper limit, which is 2 pi, because that alpha now must be in radians. It cannot be in degrees, of course. Minus is substitute for alpha 0, lower limit. So 2 pi minus 0 is 2 pi, right? So this integral here gives me 2 pi. And then, so from this I got 2 pi, and here you see 2 pi in denominator. So this 2 pi and this 2 pi will cancel. Did I answer your question?
Oh yeah, that I get it now. Yeah.
Yeah,
Thank you.
yeah, very good. Yeah. So now hopefully this result is now clear. And I would like to now make two approximations. Look, it would be an interesting question to see what is the electric field at the center of the ring at this point, when Z is equal to 0. So if you substitute in this expression Z equals 0, what do you get? Look, 0 is in the denominator, but also in numerator. So when you substitute for Z equals 0, the numerator will be 0. 0 divided by whatever is 0. So at the center of the ring, where Z, and that is easy to understand because look, because let's say this chunk of the charge produces electric field away from it in this direction, right? That would be that field dE in this direction. But this chunk of the ring on opposite side will produce electric field at the center in opposite direction. And these two fields will cancel. And the same you can do for any chunk. Let's say for this chunk will produce electric field in this direction. but the opposite chunk will produce electric field in this direction, right? Because electric field is always away, radially away from the positive charge. So you see, that should convince you that the total electric field at the center of the ring is equal to 0, which is consistent with this expression. Now, the second approximation, which I explained here, is what is electric field when Z is very, very large? So if Z is much, much larger than the radius of the ring. So imagine that now I want to find electric field very, very far away along the Z axis, so that Z is much, much larger than the radius of the ring. Then look, let's make this approximation. So when Z is much larger than capital R, then the capital R you can ignore compared to Z squared, because Z squared is much, much larger than R squared. So that R squared you can ignore, and then you have Z squared to 3/2. So this 2 and this 2 will cancel. You have Z to 3. And this Z is Z to 1. So this Z and that 3 will become now 2. And the final result will be given by this expression, 1/4π∈Q divided by Z squared. So at a very large distance from the center of the ring, the electric field is now 1/4πε0, which we used to designate the letter K, Q divided by Z squared, which is a very interesting result, because the same result you would get for electric field if the entire charge of the ring is located at the center of the ring. If that entire charge, capital Q, would be the center of the ring, the electric field at point P, very far away from the ring, would be the same, right? Because it would be the total charge times now divided by square of the distance, divided by Z squared. So when Z is much larger than the radius of the ring, the result is the same as if the total charge of the ring is located at the center of the ring, which is this result. Any questions about these approximations? I hope this is clear. It's slightly something even much more complicated, and my
Professor, you just cut off.
Yeah, my internet is again unstable. So you know what I'm going to do? I am going to shut my camera and because my image is not needed, but that should help a little bit. So let me do that. But to do it, what I have to really do is. Can you hear me right now?
Yes.
Yes. Yeah, okay. So hopefully we survive a few more minutes. But at my household, maybe my wife or somebody else is using the internet, and we have many devices. So maybe that's the problem. Anyway, hopefully everything will be okay. So now on this slide, I'm trying to I will be calculating now electric field produced not by the ring, by a disk of charge. So imagine that we have a disk, very thin disk, and that the charge on that disk is positive, and that disk, that positive charge is uniformly distributed on the disk. And so the radius of the disk is given, capital R, radius of the disk will be given, and charge density, but surface charge density, because now the disk has certain surface, so we defined surface charge density sigma is given as well. So the given quantities are capital R, surface charge density, and this distance Z, which is the distance from point P at which I want to calculate electric field from the center of the disk. So that point P is just above the center of the disk. Z is given as well. So like in previous example, Z is constant. And I will call this axis my Z axis, okay? So X and Y would be now in this plane. So the disk is in X, Y plane. And I want to find electric field at point P located on the Z axis, and P is just above the center of the disk. Now this question is complicated, but it's not overly complicated. So I don't want to scare you. I just want you to concentrate and listen carefully how we solve these type of questions. Now, for this type of questions, we could use now double integrals, but I know, which would simplify the solution. But I know that in your calculus 2015, you didn't get yet to integration over now double or triple integral. So calculus, single variable calculus. But again, this is a little bit complicated. But the trick which I'm going to use is extremely important.
Professor, you cut out again.
You see? Oh, I'm so sorry.
It's okay.
I hope you can hear me. So I will, I will stop share for a minute, and I will stop video. But I will still share the screen to my lecture notes. Hopefully that will help a little bit. And at my home, I have Bell, which is fiber optics, so it should be extremely fast. And I'm paying a lot of money for that every month. So I am very shocked that, but I am sitting in the basement of my house, and I'm using these pods everywhere in the house. So I think that maybe that is the root cause of this slowness. But I think that maybe somebody else is using the computer, and maybe some other devices at my home. Anyway, that's the explanation why this internet is unstable, I think. I hope you can hear me now.
Now we can hear.
Yeah, good. So we divide the disk into many very thin rings. Here you see that one yellow ring, okay? And the radius of that yellow ring is lowercase r. The radius of the disk is capital R. And the thickness of my ring is I called dr, differential dr, because my ring is now of infinitesimal thickness. dr approaches 0. Okay, so that's what I'm going to do. Now I'm going now to use the result which we just derived. On the previous slide, we derived this expression for the electric field at point P, a distance z from that ring. So one single ring produces this electric field, that constant 1/4πε0 z q, where q is the total charge on the ring. On the previous slide, I used capital Q, but now I'm using lowercase q. Lowercase q is the charge on one ring. Capital Q will be charge on entire disk. Okay, so sigma would be capital Q, total charge on the disk, divided by total area of the disk, which I hope you know is pi capital R squared, the area of the circle, right? So that would be surface charge density. So the charge on one ring is now designated by lower letter q. Okay, and oh yeah, and I made one mistake, that capital R should be here, lowercase r. Radius of that ring is not capital R, but lowercase r. So please make that correction. So here, okay, that should be lowercase r, which I have rewritten now. So this expression, which is electric field due to one ring, I have rewritten here, but in differential form. This is the key point for you to understand, that instead of Q, now I call it dq. That will be the charge on the ring, because that charge on one ring is much, much smaller than the total charge on the disk, right? Because the thickness of the ring dr approaches 0, so that charge on each ring I have to designate in differential form dq. And the electric field produced by one single ring will be tiny compared to the electric field produced by entire disk. So that electric field due to one ring, I also designate now by differential notation dE. So that's what I did. Instead of Ez, I write now dE. Instead of Q, I write dQ. And I understand that electric field is along the Z direction, as I explained before. So I didn't put here that Z subscript to just simplify the notation. Any question, and you see this is now correct. This, that the lowercase r is the radius of the ring, not of the disk, by the radius of the ring. And Z is constant. Remember, Z is not variable. Z is the distance from point P to the center of the disk. So any question so far? Okay, no question, that's really good. Now, the most difficult part, I hope you can hear me. Still, could somebody confirm?
Yes.
Yeah, we can hear you.
Good, yeah, and thank you very much, because I'm so nervous about that internet instability that I almost cannot teach and think all the time about that internet connection. So anyway, so this is that differential electric field due to one infinitesimally thin ring. But now what I have to do, I have to now integrate over the entire disk, right? So I divide this disk into infinite number of this little ring, and I will have to integrate over the entire disk, and I will select the variable r to do that integration, that lowercase r, right? So that lowercase r for little ring, lowercase r will be now almost 0, and then the rings will become bigger and bigger and bigger until they become capital R, until lowercase r goes to R. So the limits of integration will be from 0 to R. The only problem, and this is the most difficult part of the solution, is in terms of lowercase r, because I want the lowercase r to be my variable for integration. Now, how to do it? This is explained in this part. This is the most difficult part of this solution, and I hope that all of you will understand this today. So look, what I have to do is this. If I'm going to use now this projection, this view from the top of that disk, and that one ring is now use the color green, not yellow as before, but green. So here you see this is that one ring of thickness dr. Dr approaches 0. Okay, it's very tiny. And the radius of that green ring is lowercase r, and the radius of the disk is capital R. Now, because the surface density on the disk is given sigma, sigma is the surface charge density, then I can do the following. Now, please listen carefully. That sigma I can write like this: the amount of charge on one ring divided by the area of one ring. What is the area of one ring? Right, so sigma can be written dq over dA, or it can be also written as capital Q, total charge on the disk, by pi r squared, as I've explained previously. Right, that is the sigma. Now, but what is dA? The differential area dA, that's the area of that green ring. And that area of the green ring, you can calculate like this. Look, if you cut that ring, if you take the scissors and cut that ring and make it straight, that when you straighten that green, you will get really, when you straighten it, you will get a rectangular area, or a little rectangle, very long rectangle, for which the width is dr, and the length of that strip will be circumference of that ring, which is 2 pi r. 2 pi r. Okay, so as I'm saying, cut that green ring with the scissors and make it straight. Then you get a rectangular area. This rectangular area, for which one side of the rectangle is equal to thickness of the ring dr, and the other is 2 pi r. Then the area of that ring, that the area taken by that ring, is 2 pi r dr. Right? The area of the ring is one side times the second side. So 2 pi r dr, that's the area dA. That's this area dA taken by one ring, dA, the area dA. And then from this expression, dq is sigma times dA. So sigma times 2 pi r dr, that's dq. This, you see, instead of dq, I have written sigma times the area dA, which is 2 pi r dr. Then I have the expression for the differential field written in terms of just one variable, lowercase r. Because z is constant, sigma is constant, epsilon 0, 4 pi, these are constants. And I have to integrate this expression over r. So that's what I have written below. I took all constants in front of the integral, right? 1 over 4 pi epsilon 0, 2 pi sigma z, these are constants. And I integrate this expression, which contains variable r dr divided by r squared plus z squared 3/2. And the limits of integration will be from 0 to capital R, because that lowercase r, radius of the ring, can change from 0 to capital R. And this integral is relatively trivial integral to do. You did these type of questions in calculus 1014, probably routinely, because you can solve, you can find that solution by substitution. So here I substitute letter u is equal z squared plus r squared. Then du is equal to r dr. And you see r dr I have here, r dr I have here. So instead of r dr, I can write du divided by 2. And instead of r squared plus z squared, I write letter u, right? Because I made this. So instead of this, I write letter u. So again, instead of r dr, I write du divided by 2, because r dr is du divided by 2. And this will be u to 3/2. So this is that integral now here, written. Constants I have in front, 1/2, right? Because it was du divided by 2, and u to negative 3/2, negative 3/2. Can you still hear me?
Yes.
Yeah, thank you very much. So because that u to 3/2 was denominator, so I took it as u to negative 3/2. And I changed the limits of integration, because now initially integral was written instead of a lowercase r. So when lowercase r is equal 0, then u will be z squared. But when the lowercase r upper limit was capital R, then u will be z squared plus r squared. So here are new limits of integration. And then this integral is trivial, right? So remember, I'm using this integral. So u to n du is equal u to n plus 1. You know this by heart, I know, divided by n plus 1, right? This integral, where n is equal negative 3/2. So the integral will be equal negative 2u to negative 1/2, right? Because negative. And then substitute upper limit and lower limit, do little manipulation. And this is the result. And then I changed that, I took z in front of the integral, in front of the bracket, so that when I take z out of the bracket, then this z and that z which I took out will cancel, but then I have to multiply this term by z. So this is the final result. The final result is written, and it's very important that you redo my calculations at home from the start now. And if you are able to redo my calculations, then that will mean that you really understand how to calculate electric field due to the ring. If due to the disk, I should say, if we know the result of electric field due to one ring, like this one. So then the calculation can be done in just simple single variable. You don't need multiple variables or multiple integrals. So now, before you ask all your questions, I have no time. So what I did on the on the next slide, and it will take me only a minute, on the next slide, I have rewritten that result for two approximations. When the radius of the disk is very, very large, so much larger than Z, then Z here can be cancelled compared to R, because R is much larger than Z, and that will simplify to this expression. But because R is much larger than Z compared to R is very small, so this will become 0. And then the final result in this approximation, when R is much larger than Z, is that disk will be infinitely large, and then electric field will be the same, sigma divided by 2 epsilon 0, which we derived dividing the plane into line of charge. So we got the same result under this approximation. So I will review this concept next time. And if you have any questions, please wait. But at this point, I would like to stop recording. So I will stop share and